In the last segment, we looked at what happens when a wave hits a boundary. And what I want to do is this. At the wave machine, there's a boundary at each end. It's the end of the medium. So when I shake away from this side, it hits this end, and it bounces. It reflects and comes back. So now I'm going to put a continuous wave in at this side. Continuous wave traveling this way, hits the other side, and this wave comes and comes back toward me. And let's look at what happens where the two waves overlap. I've got a wave going this way and a wave going this way. They're exactly the same. What happens where they overlap? Let's take a look. Oh yeah. And what I get is a special kind of wave we call a standing wave. The wave's not going anywhere anymore. It's just waving up and down in place. It's waving up and down in place. So what happens is this. The interference, the superposition of a wave traveling to the left plus a wave traveling to the right is this wave that stands in place, and it's a so-called standing wave. And you get standing waves on systems where you have boundaries. And there's two different types of standing wave systems that we'll look at in the chapter. We're going to look at standing waves on strings and standing waves in tubes. And on strings, it's a string wave, and in tubes, it's going to be a sound wave. And let's look at examples of these two types of standing waves and explore the properties. I have a driver which is shaking this end of the string, and it sends a wave down to this end. There's a fixed end here. The wave reflects and comes back. So it's really fixed at both ends. I'm shaking a wave down the string. It bounces and it comes back. The constructive and destructive interference between the waves traveling in two directions gives us this. I end up with regions on the wave where I have a lot of motion, and we call these regions antinodes. I end up with other regions where the wave is not moving the string at all. This is a so-called node. So there's a node right here in the center, and there's two antinodes. Now the wavelength of this wave is this. It's the length of the string, because if we look at a slowed down version of the wave, what you can see is this. It's going up on one side and down on the other. And so the wavelength of the entire wave is just the length of the string right here. So the wavelength is the length of the string. I have antinodes. I have a node in the center. This distance between successive antinodes is 1/2 of a wavelength. That's one of the relationships for standing waves on strings that you'll see in the chapter. But now we're going to change the frequency because there's different possible modes of the string. And if I take the frequency and reduce it, I get this mode right here. And this mode is longer. This is longer. And this is the one that we call mode number 1. This is the one we call mode number 1. This is the first one. This is the lowest frequency that I can get. So this is mode number 1. And we have a question for you. The previous mode that we saw was mode number 2. This is mode number 1. Mode number 2 had a wavelength equal to the length of the string. What's the wavelength of this mode? We'll give you some choices. For this mode of the system, this is mode m equals 1. This length is 1/2 the wavelength, because this is only 1/2 of the wave. So the length is 2L, 2 times the length of the string. Mode m equals 1, the wavelength is 2L. Now, let's come back up to mode m equals 2, and if we crank up to mode m equals 2, that's the second mode. The wavelength is equal to L, just the length of the string. Now, I'm going to put up another mode, and I want you to think about what is the mode number and what is the wavelength. This is mode m equals 2. The wavelength is L. Next, I'm going to dial it up. This mode right here, it has antinode, 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 and it's got nodes here. What is the mode number and what is the wavelength for this mode of the system? We'll give you some choices. Well, in fact, you've probably detected a pattern. As we'll talk about in the text, the mode number is just equal to the number of antinodes. So this is mode number 1, 2, 3, 4. This is mode number 4. And it makes sense. That continues the pattern that you saw before. The wavelength is this length right here. If you think about how the wave is moving the string, this is the wavelength. So the wavelength is 1/2 the length of the string. So clearly there's a relationship between the mode number, the length of the string, and the wavelength. And this is one of the relationships you'll see in the chapter. This is one type of system that can support standing waves. There's a node at this end, there's a node at this end, and there's a medium in between which can carry a wave. But there's a different type of system we can have that does exactly the same thing. This tube right here can carry sound waves. And each end of the tube is open to the atmosphere. Sound's a pressure wave. At this end, it hits the pressure of the atmosphere. At this end, it hits the pressure of the atmosphere. And so sound waves, when they move up and down the tube, when they hit each end, the pressure does not change. This is a node, and this is a node for a standing sound wave inside this tube. And so we'll see a mode structure for sound waves inside tubes that's identical to the waves on a string that we just saw, if the tube is open at both ends. So I can set up a standing wave inside this tube. If I tap on it, you can hear there's a resonance of the tube. There's a frequency that the tube likes to oscillate at. And the frequency that the tube likes to oscillate at is a standing wave mode of the system. It's a standing wave mode of this particular system. But you can also have different wavelengths inside the tube. If I take this tube, it's a corrugated tube, and I swing it around my head, I can get different possible standing wave modes. And I can do that because there's different possible modes of the system. And depending on how fast I swing it, I can excite different resonances of this tube. Now, in the next segment, we're going to put the pieces together. We've got a wave on a string plus waves in a tube. And we can use that to understand the operation of your vocal system. We'll talk about that in the next segment.